Alright, so previously in chapter 3, we have been discussing ways to describe motion that occurs, but in this chapter, we want to start talking about dynamics versus kinematics, where dynamics is the reason or the cause as to why things move. So looking at what is the cause, forces are going to be the cause of why things are put into motion. And a force is just any push or pull on an object. They can cause objects to accelerate, and remember that can either mean speeding an object up, slowing it down, or changing its direction. Obviously, pushing something harder is going to have a greater effect in its change of motion. And also the direction of that force is important too. If you push something north, it's going to accelerate to the north. If you pull it with a net force south, it's going to accelerate to the south. So because the magnitude and the direction of the force are both important, we can represent forces with vectors. So let's take a look at this book resting on a table, and then the hand is going to be pushing it to the right. When we talk about forces and we try to find the total force that's exerted on an object, first we need to define a system. Now a system is what is accelerating when the force is acting on it, or what you're trying to study when you want to know the net force on it. The system it can be anything that you define, but you have to know that the system cannot enact a force on itself. Everything in the system is just part of the system, a closed black box, so to speak. Everything outside the system is referred to as the external world. External forces are going to define that system's motion. Now there are some various types of forces. The different ways you can move that textbook. You could push it with your hand, you could pull it with your hand, you could lift it, you could maybe tie a string around it and pull it that way. Those are all different types of forces. Notice that every one of those types of forces, you have to be doing something that involves touching the book. So those are all referred to as contact forces, the ones I just mentioned, and that's when an object from the external world touches the system. On the other hand, we have field forces. These types of forces affect objects whether or not the object is in contact with the other object. So for instance, gravity's pull due to Earth pulling on the book, that's going to be a field force because the Earth doesn't have to directly touch the book for it to experience gravity. Some other field forces, if you take a minute to think of them, forces that act at a distance, you have gravity. Some other forces that act very similar to gravity are going to be the magnetic force and the electric force when we talk about that next semester. So every force we define in this class is going to have an agent or something enacting the force, and it's also going to have a system that it's enacting the force on. So there has to be two players every time you have a force. You need an agent and a system. So pushing the book, the agent is obviously your hand doing the force, and the system that is being acted upon is the book. If you were to drop the textbook, in that case you're not putting a force on the textbook, only the Earth is. So the agent is the Earth and the system is the book when we're talking about the force that gravity pulls down. Notice that when you're pushing the textbook, the force of gravity is still acting on that as well, but we were just comparing a contact force to a field force. So in order to help us find the net force or the total force on an object, free body diagrams are going to be extremely helpful. So it's very important to practice drawing these and recognizing what your system is, and that's going to be the first step. You want to make sure you determine what the system is. What are you actually trying to find what the net force is on something? So that object can be represented as a particle as small as a dot. I usually draw just a shape like a square, a circle to represent my object, but it doesn't really matter. All of that object's mass is going to be concentrated as if it were a tiny dot at its center of mass. So we can represent any object as a particle, and the net forces are going to act the same. So then we are going to draw those forces with an arrow pointing away from the particle in the direction of the force. And we might not know the exact size of the arrow, but you want to try to make those relatively proportional. Are they equal? Is one bigger than the other, etc.? And the direction is important as well. Then you're going to label each force with an F and then a subscript representing usually the agent of that force on the system. You need to know which direction is positive in the x direction and the y direction. So let's take a look at representing forces on a ball tied to a string. So if we had a ball here and a string holding it up, first we'd have to define our system, and then since we're saying the force is on a ball, the system right here, and you don't have to draw a dashed line around it every time. I'm just doing this to show you how we choose our system. The system is going to be that ball. So you're going to draw a dot here, or a box, or some sort of shape that you feel comfortable drawing arrows with. And then you have to consider everything. First, the contact force is everything touching that ball. Obviously, you have the string. So the string is pulling the ball upward. We're going to call that, any time we have a string or a chain or a rope, that force is going to be a tension force. So I'm going to label that force of tension. Obviously, the ball is not accelerating upward, so we know that there has to be a force acting downward the same magnitude. And we know that gravity acts on everything. So that force of gravity, which is also the weight, is going to be acting downward. No forces are acting to the left and the right. And then you want to make sure you call the up direction positive. Sometimes you want to just make sure you know the acceleration, because if you know the acceleration, it's going to help you define your forces. So not a number necessarily, but whether the acceleration is 0, is it pointing upward or to the left. If you know where your acceleration is pointing, your forces should follow suit. So let's look at a ball held in your hand. You're obviously holding a ball here. The gravity is still going to be acting downward. It's not accelerating through your hand, so you know that your hand is supporting it upward. That's a support force, or we're usually going to refer to that as a normal force. Normal meaning perpendicular. Because our acceleration is 0, our forces must cancel out. And the normal force is equal to the gravitational force. Again, it doesn't have to be represented by the dot, but it does make it easier so you don't have to break out your artistic skills and draw a nice fancy diagram. You can just draw a dot with 2 forces labeled on it. And again, we have to decide the coordinate system. I'll just call up positive. So experimentally, we can show that the acceleration is equal to the force divided by the mass, or F equals ma. This is known as Newton's second law. And what that's saying is the acceleration is directly proportional to the force exerted on an object. So if I double the force, I double the acceleration. If I make the force only half, I make the acceleration half. In the same way, the mass wants to resist acceleration. So if I put an acceleration on an empty shopping cart, or if I put a force on an empty shopping cart, it's going to accelerate a lot more than would a full shopping cart. If I double the mass, the acceleration goes down by half. So these are inversely proportional because as one goes up, the other goes down. The SI unit for force is the Newton, which is about the weight of a quarter pound on Earth. 1 Newton is the force that causes a kilogram to accelerate at 1 meters per second squared. And again, 1 Newton is equal to 1 kilogram times a meter per second squared. Now we want to look at, I've been talking about and referring to net force. We want to look at how we add those net forces together. So in this case, we look at our vector sum of all the forces acting on an object, in this case the table, and we're going to call the right our positive direction. We have force 1 being pushing the table to the left, force 2 pushing the table to the right. Those two are going to cancel each other out, and the table is going to have 0 net force, thus having 0 acceleration. And I should point out that this force here is the net force, not just any force on the object, as we'll see in some further examples. So if we have two forces acting in the opposite direction, we have 0 newtons for our net force. Let's say they both act together, pushing the table, and they both put a force of 100 newtons on it to the right. Our net force would be 200 newtons to the right. And if the person on the right put a stronger force of 200 newtons on the table, and the other person still kept constant 100 force to the right, the net force would then be 100 newtons to the left, or since we defined our direction as positive, it would be negative 100 newtons. So that's why we're referring to the net force. The total sum of the forces is what acceleration is going to be equal to divided by the mass. So this little sigma here represents the sum or the total of all the forces acting on that mass that's going to give it its acceleration. So this just means basically the sum of the forces equals ma, or the net force equals ma. So let's look at an example here. A table has a mass of 15 kilograms. You and your friend push the table. It should be with 50 newtons each in the same direction. So we have the table, and I'm going to actually represent it as a box. You have 50 newtons and 50 newtons in the same direction. What's the acceleration of the table? Well, first we need to find the net force. In order to find the net force, we have to add all the forces on the box. So I'm going to call the right the positive direction. I'm going to take the net force. We're going to add those to 50 newtons. We're going to get 100 newtons. So my acceleration is the net force over the mass, which is 100 newtons over 15.0 kilograms. And I find that my acceleration is going to be, gotta get my calculator here, 100 divided by 15 is 6.67 3 sig figs meters per second squared.